right, so this is the Unit 2 objectives and unit overview. Remember, in this chapter we were talking about energy and states of matter. This was going to be dealing with the kinetic theory. My pen's a little too skinny. Let's go with that one. The first one is relate the observations of diffusion to particle motion and collision in gas and liquid phases. Go ahead, and what is the definition for diffusion? All right, so diffusion is the movement of particles from a high concentration to a low concentration. The reason why particles will pick up speed is because there are collisions between particles that transfer the energy from a fast-moving particle to a slower one. So let's say that the red ones are fast-moving and the blue ones are slow-moving. So at the initial condition, our blue ones are moving at a speed of, let's see, they have a slower speed, and our red ones, let's say, have a much faster speed. All right, so when our faster moving particle slams into, and I drew all of these, not even going to bump into one. Let's say that this one, I'm going to change the whooshes on this one. That wasn't very smart of me. So there's my red particle. And this time it's going to go and it's going to slam directly into that blue one. So when it goes and hits this blue one, it's going to transfer the energy to the blue one so that it's going to pick up some speed, which means it's going to now go a little bit faster. The red one is going to be slowed down a little bit because it lost some of the energy. Remember, energy is like matter. It can't be created or destroyed. It's just going to be transferred from one thing to another. So in the final condition, the red one will be going slower, and the blue one will be going faster. This one I don't see that anybody's having any problems with, and that's relating observations regarding the addition of energy by warming to increase particle motion. So right now, go ahead and write down, when we add energy by warming, what will happen to the motion of the particles? All right, so when heat is added, the energy is used to speed up particles. From Chapter 3, we know that this increases the thermal energy of the substance. All right, so I'm going to draw some boxes here, and let's have you try to see about the arrangement of particles. This is very similar to what we did in Unit 1 at the very end. But now we're going to start to talk a little bit about phase changes and what goes on there. All right, so for this next one, I've drawn some boxes for you to draw particles. I'd like you to draw them in solid, liquid, and gas, and use little whooshes or arrows to show how the motion of each of the motion of the particles. Remember to also include the density of each type of substance, each phase of matter. All right, so these are the types of drawings you should have done for particle motion for the different phases of matter. So density of a solid is more than a liquid, so you'd want to draw your particles a little closer together with a little less motion. Liquid has more random motion, more random arrangement, and more motion. And in gas, we've got a very random arrangement, and we have a lot more motion. So go ahead and see if you can find a way to try to represent the particles, the connection between particles, and what needs to happen during a phase change. All right, so what I've tried to show in this video is the difference between the arrangement of particles, which leads into the phase changes. Remember, in our solid, when we were playing with those magnets, if particles are close to each other, just like when the magnets are close to each other, the pull is very strong. So these particles are held in one place, and they're kind of locked into place. With our liquid, it was a little bit more like when we had the magnets on the table, and we were able to push the magnets around, and they would flip from side to side depending on the charges, which meant that they were not locked in place at all. And of course, gases are going to have no charges between the molecules at all. All right, so the next one is to relate the temperature to thermal energy, or ETH, of particles in motion. This should be another easy one because the The higher the temperature, the greater the thermal energy. Remember, the word thermometer literally means thermal meter. Oops, it's spelled like meat. Meter. It's been a long day. All right, so what I'm going to do is I'm going to draw a couple different pictures here and kind of stop the video and change it. So at the start, the initial conditions, I've got water that's at 10 degrees Celsius, and I've got a thermometer that's at room temperature, which is 25 degrees Celsius. So the particles in the thermometer are moving fast. The particles in the water are moving slower. So now what I'm going to do is I'm going to go ahead and draw a picture of what will happen to the energy when I take that thermometer and put it in the colder water. All right, so when the thermometer is put into the water, I'm going to use green to show the energy. So when the particles inside the thermometer are going to be hitting the sides of the thermometer. When they do, they transfer the energy to the glass in the thermometer. The glass in the thermometer warms up, and then it transfers the energy again back out to the fluid. As the energy leaves, it's going to slow the particle motion of the water molecules. And what will happen is the volume will get smaller. Because remember, when my particles slow down, they're going to get smaller, they're going to get closer and closer together. And that's going to make the volume get smaller, and my thermometer will go down. So as the heat leaves the thermometer and goes into the water, the temperature of the thermometer is going down, and the temperature of my water is actually going to go up just slightly because the heat from the thermometer will be transferred into the water. But it's the difference in particle speed that causes the particles within the thermometer to get closer together, which makes the volume smaller, which means it's not going to rise as far up in the thermometer, and so it goes down. Okay, so explain the basis for the Celsius temperature scale. What are the benchmarks, or what are the important points for the Celsius scale, and why did Celsius choose them? All right, so he set the 0 degrees Celsius for the freezing point of water and 100 degrees for the boiling point of water. You're going to have to grab out your notes so you can write down the basic things of kinetic molecular theory. We said it was easy as 1, 2, 3. All right, so you should have looked it up, and it should go something like this. Particles are in constant motion. Particles travel with a certain amount of kinetic energy, and that average speed we call temperature. And that collisions between molecules are elastic, which means that they don't run down in energy. They just keep bouncing back and forth into each other, and that energy is transferred from one particle to another, but it doesn't just go away. Because remember, there's the law of conservation of energy, where energy cannot be created or lost within the universe. It can just be transferred to one system or another one. All right, let's see if we can handle this next part here. The three variables, pressure, volume, and temperature, are interrelated. Any factor that affects the number of collisions is going to have an effect on pressure. So we're going to work on predicting the effect of pressure, volume, or temperature on any of the other variables. So right now, hold on for a second, pause, go get yourself something to eat, maybe a little something to drink, go up, walk around. If you've been watching this video, good for you. And I'll draw some pictures here, and we'll see if we can make some sense of this. All right, so pressure is a measurement of the number of collisions between particles and the sides of a container. So anything that I do that slows down or increases the number of collisions with the side of the container is going to increase or decrease the pressure. So if I increase the volume and I make my balloon bigger, the time it's going to take those particles to travel from one side of the container to the other one is going to be a whole lot longer. So I've got 1, 2, 3, 4, 5, 6, 7, 8, 9. So 1, 2, 3, 4, 5, 6, 7, 8, 9. So when I'm drawing, they're traveling at the same speed. So I'm going to try to draw these the same length tails. So I'm not changing the temperature, I just changed the volume. The time it's going to take to travel across the bigger distance of the volume means that they're going to, per second, they're going to hit the sides of the container less, which is going to result in a lower pressure. Now let's take a look at the difference between temperature. So if they're traveling at an initial speed in the first drawing, my final drawing, if I increase the temperature, I'm going to increase the speed. So these tails are all going to be longer. They're traveling faster. So again, per second, the number of times they're going to hit the side of the container is going to be more frequent because they're going to be traveling across the same distance, but they're traveling faster. So when I'm looking at pressure, pressure will go up as temperature goes up. Pressure will go down as temperature goes down. So it's a direct relationship. The next question says, explain the basis for the Kelvin scale. Use the absolute temperature scale to solve gas problems. So remember that Kelvin measures what? Go ahead and write an answer down for what is Kelvin and why do we use it. All right, so now you can see what Kelvin is. You can also see how to convert from Celsius to Kelvin, or back the other direction. So let's practice one of the combined gas law problems. The first thing I want you to do is to create the chart that you would use for a gas law problem. All right, now that you've got the chart, go ahead and fill it in from the following problem. All right, when you took the information and put it in the chart, it should now look like this. Temperature is not measured in this problem, so we're going to assume that the temperature is the same. Now next step is for you to do is to write down the combined gas law. And there's the combined gas law, P1 over T1 equals P2 times V2 over T2. Now, our temperature is remaining the same, so we can cross that out of our formula, and then just substitute our numbers in. Our pressure 1 was 100 kPa. That's going to be multiplied by our volume, which is 50 liters. Our final volume is 40 liters, and we're going to solve for the final pressure. I'm going to go ahead and solve this right here. So in order to isolate the variable, which is the final pressure, I'm going to divide by 40 liters. If I do it to that side, I need to do it to this side. My liters are canceling out. This is entirely gone. So now all I do is put this in my calculator and get the answer to my problem. Okay, your answer will be a pressure equal to 125 liters, not liters, kPa. Here's my unit. And let's see, I've got one significant figure. So when I do that to correct number of significant figures, it will be 100 kPa. The only other thing to add to these notes, since we're almost finished, is what is STP? Remember, STP is the abbreviation for standard temperature and pressure. And you're going to find standard temperature and pressure listed on your reference table under constants. Remember, pressure, we've got a lot of different units. We've got units like millimeters of mercury or torr. Or we could have kPa. We could also have PSI. These are all units of pressure. For standard temperature, we're going to use 273.15 degrees Kelvin or 0 degrees Celsius. Of course, for gas law problems, you're always going to want to have Kelvin, because for all gas law problems, you always have to use Kelvin. That's the end of that video, and we've already got one for Unit 3, so that's your whole first semester.